And the microphone is muted for all that. Okay, that's fine. Now, since there are those examples there, I will be going through some of those. We'll be going over variables today. So now we're opening up a whole new power, a whole new scape of play. Now, instead of simply having this declarative world where we say circle goes here, fill it with this color, we now have memory. We can now do some math. We can save our states. We can this will build us a bridge to having animations or having change and effect happen over time, which is great, which can perhaps lead us into interesting animated adventures like this, like shown in this GIF. Does anyone recognize this game? It's one of the more beautiful games you can play. This is Manifold Garden. And this is a game about exploring procedurally generated, so algorithmically generated architecture in an Escher world. I love interesting computational media artifacts like this. There's a lot of human practice of architectural knowledge embedded within algorithms. So algorithms, like we talked about before, recipes, procedures, a way of describing how something works for someone else to use. In this case, a bit of architectural design. Room layout, room placement, how things should look, how things should look in unison. I think it's all quite fascinating. And we'll look at a few other examples as the course goes on of this. All right. We're going to delve a little bit more into how computers work right now. I'm sure many of you have heard of processors before, right? These are the sort of beating heart of a modern computer, anything computational. They're in everything from your laptops to high-end supercomputers. They drive artificial intelligence generation. They drive robots. They also have various strengths and power levels and resource utilization and different capabilities. So the ones we often talk about, like the ones that you often hear that are made in Taiwan, those are the highest end chips. They run, at instructions in the billions per second into the gigahertz range. Now, if you have, let's say, a small low-powered chip that helps you control your electric seat in your car, those may run only at a kilohertz or 1,000 times per second, or in the megahertz, or 1,000,000 times per second. The more power, the more speed they have, the more resource utilization and the more heat they create. So there's a use case for having super fast, blazing, hot, fast processing. And there's also a need for low power processing for things that are like in an outdoor weather station that you actually want to conserve power as much as possible. Or the processors that control things like solar lights. You don't want those eating up all your battery, and they don't need to be that responsive. But they just need to do a little bit of computation when necessary. Right? So processors at their heart, what they really do is they just execute instructions. They collect a bit of data from here, a bit of data from there, and do things like add it together, or move this data from point to point. They are incredibly complex, but a lot of that complexity really boils down into doing simple things very, very quickly. And sometimes even doing multiple simple things at a time. So it also stands for CPU. So processor is short for CPU, the central processing unit. This laptop here has several processing units in it. It has a graphics card. It has audio card capabilities, audio functionality. It has a processor to handle the voltage and voltage regulation. It has a lot of tiny processors in it. I'm pretty sure my mouse has small processors in it because it handles laser. It has a little laser that shoots and then reads the It has a little camera that reads the laser feedback, and that's how it tells relative position on the mouse. It looks at small slices of laser imagery to see how far you moved in which directions. Right? This dock cam, I'm sure, has some processing power in it. A small processor. It does some sophisticated things, has like a digital zoom knob. It knows when you go up, like how to power itself on. It has a little bit of detection capabilities. So we have small bits of processing all around us. So central processing unit. How many of you heard of multi-core processors? Like when you're buying your fancy laptop for school, right? What does that mean? Does anyone know? Is anyone a computer enthusiast, PC enthusiast in the house? Oh, no one's putting together their sweet gaming rigs? I do. Surprise, shock, and dismay. So this is in one physical unit. There's actually multiple processors happening. There are multiple processors laid out on the same die, which is the term for the silicon substrate that processors exist in. And there are multiple of those, and they can each run independently. But they all do their instructions in terms of talking to memory, of doing simple math operations, and moving stuff around. So basically little organizers, little math machines. And so that's sort of like really the basics. They read, they move memory, and they do math. Each processor can be special case used, as sort of we talked about, for particular purposes, right? So the graphics processing units, like in your GPUs, NVIDIA, ATI, you may have heard some of these name brands. Intel makes graphics cards as well. Graphics cards are different from your normal general purpose processor in your PC because they are tailored. Their physicality, their way they process operations is made for graphics data, for matrix multiplications. It's made for taking a stream of things that look a lot like numbers and doing the same operations to those numbers over a broad swath of those numbers. So it's meant to do that really fast. But it's not very good at saying, hey, compare these two things, and then if it's true, do this other thing. They don't do sort of that conditionality well. So each one of these processor types have a trade-off. Physics processors, you may have seen some of those over the years. So there's actually physics cards as well as graphics cards that can handle physics simulations on your computers. And we have digital signal processing chips for the audio heads in the room that help manage digital sound. There's digital to analog converters for sound. It's all very interesting, fascinating. We'll cover some of this later in the class. You may have heard of tensor processors. Those are sort of some special purpose processors for doing artificial intelligence tasks, particularly neural networks. Yeah, you've heard of those? Yeah. They're fun to play with. Right, so these are sort of like the heart. They are the ones that actually manage, just like a mechanic, manages an engine and checks things over and is the person that reconfigures the things to make the car work. Automotive tasks. So this is the brain behind this entire operation. Now memory, on the other hand, is a huge storehouse. It's a bunch of boxes. A lot of boxes. So how much RAM does your laptop have? 16 gigabytes? 32? Those are common numbers. Sometimes you get 8, sometimes you get 64, right? Each gigabyte is over 1 billion bytes. So as we talked about before, like the number, like the red, green, or blue values, that's 8 bits or 1 byte. You could store on your machine, 16 billion of those 0 to 255 values. That's a lot of colors, right? You can do a lot of work. You can save a lot of things with this chunk of memory. So you can see these as sort of like the large box warehouses. So enormous list of numbered boxes, and they each can store information. But information has several different forms. We talked about one form, which was the integers, the whole numbers. There's another form which includes negative numbers. There's another form that includes decimals. So you can have something before and after a decimal point. Those are called floating point values, where the decimal point can float around. There's an interesting set of math based on exponents that allows those to work. So what we have here are a bunch of addresses. So we want to know the locations of each box, and each one of those boxes, which is an address, has something in it, has a value that it's associated with. So if we want to get the value 3, we can go to box 000, open that box, and there's a 3 inside. Box 1 has a 17. Box 2 has a 2. So you can start thinking of computer memory as sets of boxes with things in it. Boxes can be different sizes, like we talked about. A bit, a nibble, a byte, a word, a double word, a pretzel. And just in more than numbers and floating points, you can also store text, images, sound, video, weather reports. Everything a computer processes over or has been like shown to you on your phone has a data representation, has a box useful for it. And some larger things just contain collections of multiple boxes. Like if you go to IKEA and you want to build like a couch, you end up getting like three flat packed boxes to take home and you build those together. Well, maybe a weather report comes in several boxes that are just associated with one another. Classic storage. Programs are lists of instructions. So much like our recipe metaphor from before, programs are the step-by-step. Preheat oven, mix in a mixing bowl, mix the flour, eggs, sugar, whatever for your bread. Making brioche, I guess, because we added eggs. Cook, take out, right? So that's your instructions, right? But recipes, they live on a page, right? They're written down, they're recorded, they take up space. So programs also